Modern end-to-end autonomous driving architectures handle everyday traffic with high reliability, learning to match patterns from vast datasets. But in safety-critical, long-tail scenarios, where supervision is sparse and ambiguity is high, pure pattern matching breaks down. Current industry trends attempt to solve this by attaching a large language model to the perception stack. This uses free-form chain-of-thought text to force the vehicle to reason about its surroundings before committing to a maneuver. However, treating vehicle reasoning as a natural language processing problem allows for causal confusion. The model's internal narrative disconnects from the physical steering vectors. Under these conditions, the model can generate a logical explanation for braking while simultaneously commanding acceleration into an intersection. Alpamayo-R1, developed at NVIDIA, addresses this by establishing a mathematically grounded link between perception, reasoning, and the resulting physical trajectories. This system integrates three core components: the Chain of Causation dataset, a dual representation architecture, and reinforcement learning post-training. Safe autonomous reasoning depends on the mathematical alignment of the AI's internal logic and its physical control outputs. Previous models struggled because their training data allowed for causal leakage. When trained on free-form annotations, an AI can inadvertently reference future, unobservable events to justify its current reasoning. The chain of causation methodology fixes this by applying rigid structural formatting to the training data. The first rule, causal locality, requires splitting every driving sequence at the moment a decision is made. This quarantines evidence to the historical observation window. The model can only use information from the 2 seconds prior to the keyframe. The second rule is decision grounding. This prohibits vague descriptions of behavior. Instead, the reasoning output must map directly to a closed set of concrete driving decisions, such as a yield or an in-lane nudge. This formatting transforms the thought process into a verifiable mapping, linking past visual evidence to a specific future physical action. Managing the logic is only half the battle. Onboard deployment requires processing 360-degree multi-camera inputs over time, creating a massive influx of visual data. Standard single-image tokenization scales linearly with the number of cameras. This produces too many tokens for the context window, which prevents the model from reasoning in real time. To maintain efficiency, Alpamayo-R1 uses multi-camera tokenization architectures like triplanes or Flex. These project multiple feeds into a unified 3D grid. This intermediate representation reduces the number of sensor tokens required to represent the environment by up to 20 times. These compressed tokens are then fed into the core vision language model backbone, Cosmos Reason. Efficient vision token compression allows the model to process enough environmental data to reason in real time. A vision language action model faces a dual requirement. It must generate discrete text logic while outputting continuous physical trajectories. Alpamayo-R1 manages this through its dual representation architecture. During training, physical trajectories are quantized into 128 discrete tokens for acceleration and curvature. This couples text logic with vehicle control. Both exist in a common token space, enabling joint learning. However, autoregressively decoding 128 tokens one by one is too slow for the 10 Hz frequency needed for physical vehicle control. For inference, the system utilizes a flow-matching action expert. This decoder bypasses the slow token-by-token generation. It uses the model's internal KV cache to instantly generate continuous, kinematically feasible waypoints. Onboard testing confirms that this flow-matching approach maintains the speed required for real-world hardware execution. This dual representation bridges the gap between training in a language space and executing in a continuous, physical one. While supervised fine-tuning establishes the format for sentences and trajectories, the model can still produce logically inconsistent outputs where the text and the trajectory do not align. This creates a gap where the vehicle's text trace explains it must stop, while physically executing a smooth roll through a stop sign. To align the model's logic with its physical actions, the system undergoes reinforcement learning post-training using group relative policy optimization. The model is graded on 3 specific reward signals, beginning with reasoning quality. An external large reasoning model acts as a critic, comparing the text explanation against the scene's visual context to ensure the logic is causally sound. The second signal targets reasoning action consistency. If the physical meta-action, such as accelerate, contradicts the reasoning trace's decision to yield, the reward drops to 0. The third signal evaluates trajectory quality. This tracks L2 deviation and penalizes the model for virtual collisions or high jerk movements that would be uncomfortable for passengers. These rewards ensure that the resulting system is not just a fluent text generator, but an aligned reasoning engine bound by physical laws. Closed-loop simulations demonstrate the impact of this alignment. When facing a construction barrier, the aligned model correctly identifies the hazard in its reasoning trace and initiates a physical nudge maneuver to avoid it. The data shows a 37% improvement in logical consistency and a 35% reduction in close encounter rates compared to baseline models. This entire deliberative loop runs in 99 milliseconds on onboard compute. These results indicate that scaling datasets and model parameters is only one part of the solution for Level 4 autonomy. Genuine progress in autonomous driving requires an architecture that mathematically binds internal causal logic to physical control.